We've learned that in order to make an object move around a circle, you must always push it perpendicular to the velocity. Another way to think about this is to say, the force you apply, the net force, is always directed toward the center of the circle. To see this in action, let's watch this student use a broom to move a bowling ball in the circle. So here we go. Here comes the bowling ball, and he's going to try to move it around in a circle. And watch how his broom hits the ball. Which way is he hitting the ball? What is the direction of his force? You can see that the direction is perpendicular to the velocity, or in toward the center of the circle. Let's see one more time. He's always hitting it toward the center of the circle. We've seen this already. If you have an object moving around a circle, the velocity is always tangent to the circle, and the force is always in toward the center of the circle. Now, we know that Newton's second law says net force is equal to mass times acceleration. Force is a vector, acceleration is a vector. So if an object feels a net force, and this object moving around the circle, it does feel a net force, then it also must accelerate in the same direction. What have we learned? Objects that move around a circle accelerate toward the middle of the circle, or toward the center. And this is a really important principle. Even if the even if the speed is constant, is the velocity constant? The answer is no. And the reason is because velocity has direction, and from one moment to another, the direction of the velocity is changing. We can see that. The arrow swings around. So at this point, the velocity points left and would be negative. Down here, the velocity would point right and be positive. So the velocity is not constant because direction changes. This is a big idea, and sometimes it's hard to understand. So just briefly, let's consider the following scenario. We've got an object moving around a circle, and here it is when it's at the bottom. The velocity points like this. We'll call that VI. Then, at this later moment, we have VF. We know that delta velocity, change in velocity, is final velocity minus initial. We also know that we could add VI to both sides, and we get this. So what does the equation say that we just wrote down? It says VF is the resultant. So consider the vectors that we've just drawn. Here's VI. Whoops. Let's draw VI again. Here's VI. And we have to add some change, some delta, so that VF looks like this. VF is the resultant. VF is tail to tail, and it will be tip to tip. So what delta do I draw in order to get VI to swing over to where we have VF? Here's what the delta V looks like. The delta V I just drew in black allows us to take VI, add tip to tail, delta V, and we arrive at the new VF. So let's draw that delta V in to our picture. Here's the start point, here's the end point. On average, we're right here, and look at what delta V does. It points toward the center of the circle. And acceleration, we know, is delta V over time. So if delta V points toward the center, so does acceleration. This is all just a really fancy way of proving that, in fact, objects moving around, when objects move around a circle, even if speed is constant, velocity changes, and the object accelerates toward the center of the circle. So we have now proven that by drawing the delta v vector and saying, hey, look, it points toward the center, just like our picture shows. And it points toward the center. If it points toward the center, so does acceleration.